I wonder, for instance, whether it's possible to avoid to build a dam by water savings. And in principle, it's possible. I told you that if you use sprinkler irrigation, provided they want to use it, you can save 60% of the water. So it's possible that we can avoid the construction of a dam by just implementing water savings. But of course, I need to solve this equation because I need to know at the end of the story how much more water I need to give to them. And this was the subject. And of course, in order to solve this equation, solving this equation, you solve the problem because you get time by time the estimation of the deficit, the estimation of how much water you need to solve the deficit. But you need to integrate it, and for this you need to specify water availability and water demands. So basically this was the first question, and so we set up a very simple model, simple in terms, in theoretical terms, but the application is not so simple. And basically we started from the water demand at the field, which means that you go over the field, people were sent over the fields to make an inventory of all the cultivations in this area, in this domain. The domain was, again, the area served by the Reclamation Consortium. So they went there and they made an inventory of all the cultivations. And then the literature tells you how much water each cultivation needs. So the literature tells you if you have a given crop, what is the volume of water that that crop needs, usually on a monthly time scale. And therefore you get an estimate of the water demand in the field. And this water demands depend on the crop, but also depends on the climate. Because, of course, the same crop in a hotter climate needs more water. Depends on the permeability of the soil. Because, of course, if you irrigate and the water flows deep into the ground, it's not available for the crop. If you have a reduced permeability so that the water is stored and kept in the upper part of the soil, it's much better. And then also depends on water availability. Why is that? Because if you give the farmer a lot of water, they use more water. Farmers, if they have less water available, they save water. So also water availability is affecting the water demand. And also the irrigation technique, I already mentioned to you. So all these features were recorded through inventories. And then there is the leakage. The leakage is a big problem because this is the water demand at the field. But you get the water usually from the river very much far apart from the field. And then you bring the water through canals to the fields. And in doing that, in doing the strip, you lose water. And the estimation of the water losses is a question mark, a big question mark. We assume, basing on experiences that we made with practical experimentation, we assume that the water losses are about 50%, which is a huge amount. But basically, this is what the experience and the experimental campaigns that we did suggest to us. So basically, if you knew the leakages, then you get to estimate the water demand at the river. So from the field, you go upstream to the river and you know the water demand at the river. And then you can apply a water balance model because once that you know the water demand at the river, you can compare the water demand with the water flow into the river. And if you detract the environmental flow, you can estimate every day if you have enough water or if you don't have enough, what is the water deficit. And therefore you get, we did this analysis at daily time scale. So each day we made this comparison at the river. The daily time scale is fine because if you did it at the monthly time scale, this is not really appropriate because you have strong fluctuations during a month. During the river, basically the water demands and the water availability don't change much because the river flow during summer doesn't change much during a day. So the daily time scale is fine. The monthly time scale with these rivers is not fine because sometimes you start in July, at the beginning of July you have enough water into the river, but then they run dry. So we choose to adopt the daily time scale, but in some cases you may need to use the hourly time scale, which means that the time step, the finite difference time step that you use to integrate this equation is at 1 hour instead of 1 day. And when you compute this water balance model, we also accounted for rainfall, because if it's a rainy day, of course you don't have irrigation requirement at the field. And also we took into account a lot of other issues, like for instance, if it happens that the river has an high flow that day, you have to account that people don't take any water, because when there are high flows during summer, the water gets muddy and they don't want to get it, because you can't irrigate the fields with muddy water. So basically, we accounted by looking at rainfall in each day and the river flow in each day. We accounted for all these constraints. These are constraints. In water resources management, you have a lot of them. Okay, finally, we get the water deficit at the river. But the water deficit at the river is not the water deficit at the field. You have, again, to pass through leakage, and then you get an estimate of the water deficit at the field. And basically, we ended up with an estimation for the given river. We considered 2 rivers, but what was very relevant, sorry, just 1 second, was this river, the first one. And basically, the deficit was about 60 millions cubic meters per year. And you know, 60 millions is an amount that is significant, because if you think to the size of a dam, usually the dams in Italy, they have size from a couple of millions water to about 300 millions. The Bayonne Dam was about 250 millions. So 60 millions at the field, which means about 100 millions at the river, it's a significant amount. And therefore, you know, people, the farmers, the stakeholders concluded we need a dam for this. Let me just conclude. And what are the strategies for solving this problem? The dam, and I tell you later why the dam is considered a solution that is not optimal, or other solutions could be water savings, because you know, we know that in the canals we lose about 50% of the water, and in the canals for leakage, water losses. And also we know that by using flood irrigation we have a consumption of water which is much relevant. So if you make a computation, basically you have at the field a deficit that is about 30 millions. 30 millions, if you avoid the water losses, you would go down to about 10 millions. So 10 millions is a reasonable amount of water, 10 millions of cubic meters per year, which one could find by using small storages. An alternative idea here was to use small storages, because small storages are, you know, are less impacting in terms of environmental impact than a dam. And this was a solution. Another solution was to use sprinkler irrigation. And you see a picture here. This is a picture of flood irrigation. You see the result. You can understand why you have a high consumption of water. This is flood irrigation. This is sprinkler irrigation. The problem is that people didn't want to use it, even if one said that the public administration pays the money for it, because you know, the public administration to build a dam, it's a huge expense. It may be more convenient to give the money to the farmers to put sprinkler irrigation into practice. The problem is that they didn't want to use it for the reasons that I mentioned before. An interesting thing was that they then made an experiment. They selected one farm, and in that farm they used sprinkler irrigation. And then they noticed that the amount of water was, the saving was what I mentioned to you before. So they used less than half of the water. And also they found that the amount of grass that was produced in terms of weight was unchanged. But still, the other farmers said that, you know, you can never say if the flavor of the cheese is unchanged. So the next year they organized a cheese tasting experiment. And even after the cheese tasting experiment, which was negative, negative meaning that they didn't find, the expert taster, they didn't find any difference. But still the farmers are still resistant. They don't want to use sprinkler irrigation. But this is a possible solution. And keep in mind that water resources management becomes a societal problem at this level. You may find the solution, you are dead sure that the solution is fine, but your job becomes to convince your stakeholders that you are right. And this becomes really tricky, because very much depends on your ability as a speaker, to explain why you are convinced by your solution. It's really, it's interesting. And now let me just, oh, this is interesting as well. This was an experiment that was done, successful one, in a part of the region. They set up a website to assist stakeholders in irrigation, and I'm not sure if I get the connection, I will show it to you. And basically, this website applies in real time a very simple water balance model. And basically, they know for each farmer what kind of crop they cultivate, and they know the kind of soil of the farm, because they made, of course, some field data collection and data analysis, and therefore they can, by knowing the rainfall, the past rainfall, and by using the meteorological prediction to predict rainfall for the next couple of days, by knowing the crop and the type of soil, they can make a prediction for the farmer a couple of days in advance of the water flow to be granted to the given crop. And basically, it works. The farmers were a bit skeptical at the beginning, but then they realized that they saved a lot of money because they have to pay the water that they use for irrigation. They realized that they saved the money, and therefore they started using it. It's still active. It's called we call it IRRINet. And if you look in Google, you find it. Of course, you cannot get into the website because it's reserved for the farmers, but there is a description of the service. This was an interesting experience which was successful, and it granted a substantial saving. Now, let me speak about this reservoir. And I told you that farmers were requesting to build a dam and therefore a reservoir. And indeed there is, let me see if, just 1 second, I wanna, it's here. I'm not sure it is also in English, let me see. But this is the website, and no, I don't think it's in English. But basically here there is a description in Italian of the service, and you know, there is a Twitter also warning. Oh, there is English also. Information about IRRINet in English. It's a PDF. And it's an interesting, I mean, let me see if I can, it's here. And you see it's in English, and it's, this is the balance model. It's interesting to see. I mean, it's not a document for the exam, but it's interesting to see how it works. And with you see the soil water uptake and the evapotranspiration. There are some. I spotted a spelling error. Maybe it's unique because the English seems to be good. And then there is explanation of crop evapotranspiration, water table contribution, etc., etc. We are not looking at the details, but indeed it's interesting. So I told you, there is indeed in the upper part of this river, of this Apennine River, there is a place where a dam could be built. It's an ideal place because with, you know, there is a very narrow section, a very narrow reach of the river, which is also characterized by a geology that is favorable to building a dam. They thought about I don't know, I'm missing the term in English. It's not a concrete dam, it's a dam done by soil. It's a flexible dam. I think it is something like earth dam or something like that. I'm missing the word now. But basically, in this very narrow reach, by building a dam that has an elevation, if I well remember, of about 60 meters, a huge storage could be established upstream of more than 100 million cubic meters. It's about 120. So indeed, it's ideal. And what is the main concern? First of all, the first project for this dam was done about 150 years ago. And it was not because the problem was already there, and it was never realized in these, during these years, because basically the main concern is bed load transport and the suspended load in the river, and therefore reservoir siltation. Basically, it seems that, keep into account that when you try to predict reservoir siltation, it's really a challenge. It's impossible to get a reliable prediction. Either you see that the geology of the basin is clearly very unfavorable to bed load, and because they are like very strong rocks. In this case, we are in the Apennines, where we know that the type of geology that we have there makes a river bed load quite significant. To make a prediction is really tough. And there were estimates that such a reservoir in about 20–30 years would be completely silted. Other estimates, people said that the expected life of the reservoir would be close to 100 years. In any case, it would be a temporary solution. But if you think about a solution of 100 years, people are happy, because when you basically go beyond the expected life of everybody, usually people don't care. If you talk in terms of 20–30 years, then people start caring. It's a strange psychological mechanism, because people should be concerned anyway, because if you have children, they will have children that will survive more than 100 years. So it's difficult to understand that people don't care when you talk about 100 years from now. But this is to try to make an experiment. If you say somebody like hail pollution will be much heavier in 2150, people say 2150. Who cares? They don't care. This is why when you listen to prediction for climate change, you don't listen prediction to 2200. People talk about prediction for 250, maybe to 2100, but more often 2050. Why 2050? It's clear. Because if you talk about 30 years in advance, people are concerned. If you talk about 150 years, people are not concerned. So basically the concern was, that for sure, if they built this reservoir 150 years ago, now this would be a completely silted reservoir. And this was the main concern, which is still there. And it's difficult to estimate. People thought about making an experiment like digging in the river a big hole and to compute how much time is required for the river to fill it. But it's not the same situation for a reservoir. And also they thought about using innovative systems to allow the sediment transport to bypass the reservoir, but these systems are really, keep in mind that once a reservoir of this size is sealed, there is no solution. There is no solution. You can't bring the material away from it, because you don't know where to bring it, because it's mud, so who could get it? It's very expensive. And even if you open the bottom discharge of the reservoir, you cannot get the silted material through. You get a canyon in the middle of the reservoir, but you can't get the material through. And also, even if you could, there would be a tremendous impact downstream, because water turbidity and etc. So it's really something that is challenging. And also another issue that is not considered, this reservoir will be empty during summer. So it will be from a landscape point of view, it would be terrible because you would see an empty lake, which is not really a good feeling. Okay, that's it. So you can understand basically from this example what is a typical case study. And from a theoretical point of view, what is important is to emphasize that everything in the development of this case study is related to the application and integration of this equation. Keep in mind that this equation is the baseline for you. You need to know it, and it may be a classical question at the final exam, like, can you please formally write the water balance equation? Usually I don't ask it because I think it's too simple, but anyway, it may happen. So, you know, as a student, you have to make sure that you know all the stupid questions. You are able to reply to all the stupid questions, because the worst thing that can happen to you is that you make a mistake on a stupid question. So be aware of this, because it's not a problem if you fail in a challenging question. The problem is if you fail in a very stupid one. Okay. Now let me move forward to the next one. And the next step that we undertake is estimation of water resources availability. And therefore you have two possible solutions here. So again, your question now is, how can I estimate how much water is available? And let's refer to rivers, okay? So, of course, if you refer to groundwater, it's a different story. Now, our first question is how to estimate the river flow. Because water availability, when you take the water from a river, estimating water availability means estimating the river flow. Then you subtract the environmental flow, you subtract any other additional flow that you may need to leave in the river, but still you need to start from the river flow. And estimating the river flow is a challenging problem in hydrology. So you have basically two completely different situations. Either you have the data or you don't have them. Indeed, you may also have a mix, like you have a few data, but let's consider the two main ones. Either you have the data or you don't have them. And basically, indeed, it's reasonable to make a clear separation, because having data means that somebody went there and put there a river gauging station, what is also called an hydrometric station. So basically, you may have the data, or let me see, hydrometric station. It's also called the river gauging station. It's also called an hydrometer sometimes. There are several terms to identify an apparatus that has the purpose of measuring the river flow. So basically, either you have, yes, you have it, and then you have the data. Or, if you don't have it, you have no data. There are some mixed situations possible, like, for instance, there is an hydrometric station, but for some reason you don't trust the data. Or there is an hydrometric station which worked up to 1970 and then it didn't work anymore. So you are in a situation where you have the data but not enough. But let's make for now a clear separation, which often happens in practice. Either you have a river gauging station and then you have the data, or not. If you have the data at the required time scale, because as I said, you need to select a time scale to apply the water balance equation. I mentioned to you in this case study the daily time scale. So either you have the data at the required time scale, and then your problem is solved. So in this case, daily time scale, if you have measurements of the river flow at the daily time scale for a sufficient number of years, I usually give a rough indication, a rough guideline of 10 years in order to, to claim that you know water resources availability with limited uncertainty. You need observation for about 10 years, at least. So if you have this data at the required time scale for at least 10 years, you may say that your problem is solved. You don't need any technical solution to estimate water availability. But in practice, this happens very rarely. It may happen that you have an hydrometric station. It may happen because I mentioned to you that in Italy, the National Hydrographic Service started in about 1920 to establish a lot of these stations. So if we talk about major rivers, we have the data usually. If we talk about the Po River, we have a lot of data. Let me show you an example, a time series of the Po River flows. Time series means the data. I show you a time series is defined as a collection of observations along time. And indeed, for the Po River, we started in 1920 to get in several stations measurements of daily river flows. And in particular at the closure, at the last part of the Po River before the Adriatic Sea, we have, I can show you the series available, which is still measured. The only problem is to find the graph, but I think I will be able to find it. Let me see. Not this one. I will get the right one, just 1 second. Okay, this is not really the full time series of the daily river flow. It's a time series of the annual maximum river flow of the Po River. So from the series of the daily river flow, they took for each year the maximum one, and this is the resulting time series. So you see you have along the x-axis the year, and along the y-axis you have the river flow. And this is the maximum. If you look at the minimum, you see that there is an increasing trend. If you estimate a linear regression, there is an increasing trend. But it's not really meaningful because you see a lot of variability. And this is something that you have to get used to. When you see a time series of river flows, by looking at the time series, you have to get used to see the relevant features. And one relevant feature is the average value. You see here about 5,000 cubic meters per second. And this is the annual maximum. And another relevant feature is the variability. So the mean value and the variability, when you have some data and you plot them, get used to look first at the mean value and the variability, which is relevant. Because with a so relevant variability, it means that if you estimate a linear regression, it's not really meaningful. Because maybe that you get 2 years with low flow, and then the linear regression line gets flat, gets horizontal. And let me show you the minimum. This is the minimum. So if you look at the minimum, look at the average value, 600. And look at the correspondence for the Po River, it's 10%. So So the maximum was, I don't remember, 5,000, and this is about 600. So get used to these orders of magnitude. This is extremely important. And this is the annual minimum, and if you draw a regression line here, you see that it's declining. Please. You had a question?
Yeah. So if we are designing any problem, do we look at the average or the extreme values?
It depends on what you have to design. For instance, if your problem is water resources management, you look at the minimum value in a year. And if your problem is flood mitigation, then you look at the maximum. And in this case, I said look at the variability, because in water resources management, of course, you look at low flows. Why is that? Because you need water when you have low flows into the river, because when you have high flows, it means that it's raining, and therefore you don't need to take water. Usually you need to take water during the summer, when the season is dry and the river is low. So you have to look at the minimum. And one other important thing is that is variability, because, for instance, let's suppose that this was flat, completely flat, around 600. It means that you are sure that during summer you can always take 600 cubic meters per second from the Po River. In this situation, if you design your aqueduct for irrigation around 600, what happens is that in about 50% of the years you can't get that water. So this is why variability is important, because it conditions the probability of failure of your water supply system. And we will get into the details later, but later during the subject. But basically, coming to your question, the reply is that the relevant feature in your data that you need to look at depends on what you are designing. And in this case, I would look at the minimum. And the way in which you look at the minimum is that the water balance equation is integrated along summer, not during winter, just along summer. And I think it may be interesting also to have a look. Just 1 second. Because we talked about the linear regression, and look at this. This is a linear regression on the minimums, but this is an animated picture. And basically what we did here is to estimate the linear regression on the minimum over a window of 50 years, starting from the first year, moving to the last year. And what you can see is that the slope of this linear regression over the minimum changes continuously. It's red when it's decreasing, it's blue when it's increasing. And what we wanted to prove here is that a linear regression over a time series that has so relevant variability is not meaningful. Because, I mean, this is performed over 50 years. 50 is considered to be a very long time period for water resources management. But you can see that still there is this variability, which means that your design is affected by relevant uncertainty. Okay, so now let me go back to the original question. So either you have data, and basically the estimation of water demands is solved, because you can integrate the water balance equation by using your historical data. And then you can, along a time period that is as long as possible, you can compare water demands and water availability and estimate the deficit, the water deficit. But very often you are in a situation where you don't have data, and therefore you have to find alternatives. So when one refers to rivers, a very frequently used alternative is to use a rainfall runoff model, which means that starting from the knowledge of rainfall, you try to reconstruct the missing river flows. And the rationale behind this is that rainfall data are more easily available than river flow data. You may ask why. why rainfall data are more easily available. And I may mention at least 2 reasons. Rainfall is much easier to measure than river flow, much easier. I mentioned to you that you just need to take a pot and put the pot outside, and then every day go there and see what is the water depth into the pot, into the tank. So it's easy to measure rainfall and it's less expensive. Furthermore, rainfall, in terms of spatial variability, I mentioned in the previous pictures temporal variability. Get used to this difference. One thing is temporal variability, one other thing is spatial variability. Hydrological processes are varying in both space and time, both. So rainfall, in terms of spatial variability, is not highly spatially variable. River flows is much more highly spatially variable. Don't take me literally, rainfall is not constant over space. When you drive during summer, you know that you may experience a thunderstorm which is extended for a couple of 100 meters, and then you get suddenly the sun. But if you think conversely in terms of winter rainfall, usually you may drive for about 100 kilometers under the rain, which means that at least in some seasons, rainfall in space doesn't vary much. The river flow, unfortunately, is not like that. If you measure the river flow on a river, you cannot extend the same measurement in a nearby river, even if it's just 2 kilometers apart. You cannot do that. River flows is highly spatially variable. Each river needs its own measurement in several stations.